So yesterday we started with the stress and strain. Okay, we had gone through the concept of stress and strain, and we have seen what is stress and what is strain. So by definition, what we have come across is stress is resistance to deformation. That is how we define the stress, is resistance to deformation. And strain is nothing but the measurement of our deformation. Okay, is the deformation what we have in the member. And mathematically, if we want to measure the stress, okay, if we want to quantify that stress, this is the expression what we have. We express it as load per unit area, or P by A. Okay, P applied load, A the area which is normal to the load application. So that is what we have taken. And we have come across axial stress and axial strain. Only axial stress and axial strain. That is one bar we have taken, which is subjected to a axial load. If the load is trying to elongate the specimen, it is tensile in nature. If at all, if it is trying to reduce the length of the specimen, it will be compressive in nature. So accordingly, you will encounter tensile stresses and compressive stresses. Shubham, you have raised the hand. Any difficulty, doubt? Shubham. If you have any doubt, you can unmute and ask that. So two kinds of stresses may arise. The nature, what I am talking is about the nature of stresses. So we may have tensile stress or a compressive stress. Both will be expressed as sigma, which is equal to P by A, load per unit area. And the units what we have for measurement of stress are Newton per mm square, Newton per meter square, megapascal, kilopascal, or simply Pascal. So 1 Pascal will be 1 Newton per meter square. So that is the conversion what we can have. And coming to the strain is the measurement of relative change in the dimensions. Okay, we express that as the increase or reduction, the change in length to the original length. We take it as a ratio of change in length to the original length. For example, in this part itself, we have seen original length was L. After the application of load, the length has increased to L plus DL. So this DL is the increase in the length. Okay, so what is the change in length? Difference between these two, L plus DL minus L. So that comes out to be DL by L. This is the change in the length. Okay, so these are the two quantities what we encounter in the materials when they are subjected to loading, stress and strain. Okay, now these stress and strain, they are related by some means. Okay, so that relation is expressed by Hooke's law. Okay, so according to this Hooke's law, the stress is directly proportional to strain, but it has its own limitations. What? Condition that within elastic limit. Within the elastic limit, this is valid. Stress is directly proportional to strain. We'll look into this elastic limit further, but I can write this as stress is directly proportional to strain, or we can come across a equality expression taking into the constant of proportionality. Stress will be equal to E into epsilon. So this E will be the property of a material. We call it as a modulus of elasticity. Modulus of elasticity, or the Young's modulus, Young's modulus. So this is how these two are related. Okay. Only the limitation is it is valid only within the elastic limit. Okay. So this is one relation what we have as per the Hooke's law over here. One of the law what we come across in this stresses and strains. Okay. Now what is this Hooke's law? Let us go into that further. Now also, it is not sufficient if I just say or talk about stress, strain and their relation. I also need to understand the behavior of the material or behavior of any member. Okay, for that purpose, we go for plotting the stress strain curves. So normally we go for applying load on the specimen and measure the load and the deformation of the specimen And with the help of these, we can go on plotting what is the variation in stress and strain with changing loads. Okay, so this is a typical specimen what is used in the test, a tension test. Okay, so what we'll do is we'll apply load on this specimen. Okay, and we'll measure the increase in the load. This load will be increased gradually. This is the axial load which will be applied over here. So this load will be increased gradually in a testing machine, and we'll be measuring what is load and deformation. Okay, we can have that load and deformation chart, and we'll be able to measure that load and deformation here. Further, with the load and deformation, knowing the cross section of this specimen, I can determine what is the stress as well as strain. So this is what we do in that test. This is the tabulation what we come across. Okay. Now coming to this specimen first. So these will be the grip lengths. What you see here, L0 is the actual test length over which the test will be performed over here. Okay. And we'll measure the deformation over a very small length called the gauge length here. This is the actual test length. And again, in this, we'll restrict our measurement over a small length called the gauge length. Okay, so all these deformations, what I'm talking over here, will be measured over this gauge length using a strain gauge over here or extensiometer. So that will be the measurement what we'll be taking. Now, what we observe once we start the test, okay, what we'll observe is with the increasing load, you'll also find there'll be increase in the deformation. Okay, so I know what is the cross-sectional area of this specimen. Okay, that can be determined based on the specimen size or shape. Knowing all those things, the cross-sectional area will be known to us. So I can express this stress here, P by A, where P is this load. Okay, so stress can be calculated here. And also for every value of stress, we can determine what is strain, change in length divided by original length, which may be L0 or L. Okay, so this change in length will be measured as a deformation over this gauge length. So this strain can be calculated. Now, once you have all these test results, what you do is you start plotting it. Okay, so this is what a normally stress strain curve will be. Something typical stress strain curve. This is how it looks like. Depending on what material it is, it will be changing. But this is the how you plot strain taking on x-axis and stress taken on y-axis. We'll plot this stress strain curve. There are some features of this stress strain curve what we'll be noting over here. So if I take up this for a mild steel specimen, okay, which we have in our construction, we come across the steel, the most common material steel what we have in our construction. So in case of a mild steel specimen, these are some points what we have. So there are some points which are marked as A, B, C, this D point, E and F. Okay, so this point A is the limit of proportionality. Okay, this is the point where the linearity relationship between stress and strain will end. Okay, beyond this point, stress will not vary linearly with the strain. Within this point, what happens is with increasing strain, stress will also increase linearly. That is, this is a straight line here. The variation is straight line. Okay, so within this limit up to this point A, the relation is a straight line. As you increase the strain, stress will also increase linearly. So this is the proportionality limit. Okay, so up to this limit, the Hooke's law is valid. Up to point A, the Hooke's law is valid. Beyond this point A, which this Hooke's law doesn't hold good. Okay, so A is a point of limit of proportionality. Okay, the proportionality limit ends. What proportionality limit? The limit of proportionality between stress and strain. The linear relationship between stress and strain will end at this point A. Okay, now what happens if I load this specimen further beyond A? We'll reach a point called B, the yield stress or yield point. Okay, So beyond this point, yielding will start over here. Okay, before this point, A is there, wherein there is a linear relation between stress and strain. After A, that linear relation is ending. You can see there is a small curve here. Okay, if you look into this point between A and B, the variation between stress and strain is not shown in the form of linear. It is no more linear there. Okay, it has been represented by a small curve here. Okay, it is not a straight line here. So that is a small curve. Okay, so that is a yield point. So that is where yielding will start. Okay, yielding in the sense you'll not be able to recover any deformation in the specimen. Okay, so within this range, this is the elastic range. Okay, A and B. So beyond this point B, I will not be able to recover the deformation that take place in the specimen. Okay, or in the member. So up to point B, you can uh, regain the original shape and size of the specimen. Say if I start loading the specimen from here, from zero load up to this point A, proportionality limit, then beyond this, I'll come across point B. So what is this point B is, if I start unloading before this point B, I'll be able to come back to the original shape and size of the specimen. I'll be able to get the original shape and size of the specimen. Say if at all, if you have used a specimen of circular specimen of diameter 10 mm. Okay, so if I stop at this point somewhere between A and B, if I stop it and start unloading, bringing back my load to zero, I'll be able to get back this original shape and size over here. Okay, 10 mm diameter. If you measure it again, unload, measure it, you'll be able to see that the diameter will be 10 mm and it will be of circular cross section only. Okay, now if at all if you cross this point, what happens is there will be reduction in this area. Okay, the diameter will get reduced. Okay, the specimen is elongating, the diameter of the specimen or the size of the cross section is changing over here beyond that point B. Okay, but even within this A and B, or here also it will be changing. But thing is, once I cross this point B, I'll not be able to bring back the original shape and size of the specimen. That is what this yields point represents, the point B, yield point. Okay. Now, after this, we have upper yield point and lower yield point here. This is the maximum yielding that will occur in the specimen, okay, at C. And then what happens is there will be a reduction in the stress. The stress will start reducing here, okay. So it will reach a lower point, which we call it as a lower yield point. It will exhibit this property. Any mild steel or ductile material will exhibit these properties, that is upper and lower yield point. Okay, so upper yield point, it is the maximum point up to which the stress will go on increasing without much increase in the strain. Okay, there's not much increase in the strain, but stress is increasing here. Okay, once it reaches this maximum value of stress, then what you find is there is a small reduction here. Okay, there is a small reduction in the load. If you observe the load values when you are testing, so it will come up to a some minimum value, which will be the lower yield point, this D. Okay, and after that, further you will see increase in the loading. Okay, the specimen will start taking up the load. This is, there will be a elongation. Okay, without any increase in the load. This is the point what we call strain hardening. Between C and D, you will find that the deformation will take place under a constant load or under a reducing load here. Okay, the load or stress value will reduce, but strain will be increasing here in this region between C and D. Okay, so that is the strain hardening part over there. Okay, after I reach this lower yield stress, after this plastic deformation will start. Okay, so what you will find here is strain will increase at a higher rate. Okay, without much increase in the strength, you will find there is a large amount of deformation here. So this range, what you have here, this is the plastic range. If you have tried applying load or weight on a plastic, okay, so you'll find that it will just yield. With any small increase in the load, it will be yielding. Initially it will show some resistance. Okay, same is true with this steel also. So initially this resistance you will find over there after yielding, but once you cross this lower yield point, there will be increased deformation, what you will find in the specimen. Without much increase in the load, the deformation will keep on increasing at a higher rate. Okay, so this is where the plasticity will come in picture. So whatever deformation occur in this region are all plastic deformation. Okay, so what you find is in this region, in the plastic deformation or beyond the lower yield point, there is a point of maximum stress, which we call it as a ultimate stress here. Okay, so it will reach some maximum stress, then it will reduce, and then it will fail ultimately, or rupture will take place over here. So this is the fracture or the rupture what will take place in the specimen. But before this occurs, we will notice that the test specimen will attain a maximum value of stress, maximum of any of these values. Okay, that is what we call it as a ultimate stress over here. Ultimate stress is the maximum stress what the specimen will take before failing. So that is the ultimate stress. Okay, and this is the stress at rupture. At point here, the specimen will fail. This particular stage will be attained. Specimen will fail, and the stress at which it has failed, we call it as a rupture strength or the stress at the failure. Okay, so that is what we'll find here. So these are some points what you'll observe in a mild steel specimen. Proportionality limit, okay, yield point, upper yield point, lower yield point, okay, and ultimate stress and the failure point or the fracture point. Yeah, okay. So you may have some question here. Okay, if you have any doubt, question, please unmute yourself. A to F points. Are they clear? A, what is point A? Limit of proportionality. Point B is where yielding starts. It is a yield point. In this yielding range, you have upper yield point and lower yield point. Okay, so upper yield point and lower yield point. So lower yield point is a point beyond which the plastic deformation will come in. That is what happens in plastic deformation is without much increase in the load, there you'll find deformation taking place. Okay, very easily you'll be able to pull that specimen beyond this point D. Okay, there will be large amount of deformation even for a small increase in the load. Okay, so this is the plastic range, what we call. And here we will come across point E, which is the ultimate stress point, and the fracture point F, where the specimen fails. Now, when the specimen can take this stress, okay, why it will fail at a lower stress? It has taken a stress much higher than this failure stress or stress at failure. Why it is failing at lower stress then? It should be able to withstand this stress actually, fine, but it is failing over here. If it has to fail, it would have failed at this point E only. Why it is the stress is reducing here? Any answers for that?
So because of elasticity.
Elasticity is gone. Once we cross this point D, elasticity is gone. Now we are dealing with a plastic material here. There is nothing elastic now. Okay, elastic is what? It will come
So
back to
then,
its shape and size. Yes. Yes. What is other point you want to put? Elasticity
so because of plasticity,
because of plasticity is there.
it loses
Okay,
its shape.
it will lose its shape. It cannot be recorded. That is there. Okay, that is the nature of this plastic range. Okay, but what I'm asking is when you are able to take up 50 kgs, what you are not able to carry 10 kgs. The question is something like that. When it can take a stress, ultimate stress, okay, which is much higher than the stress at yield point. Why it is not failing at this higher stress only? Okay, what may be the reason? If anybody is knowing, there is one more curve. What is shown here? Yes, this is the test curve, what we calculate. Okay, conventional stress strain diagram or the nominal stress strain diagram, we have called it here. But actually, the true stress in the specimen will be something different only. This is because we will not be able to measure this reduction in the area here. When the specimen is put into the testing machine, we cannot measure at every instance what is happening to the cross section area. With the elongation, what is shown here is the cross-section area is reducing actually. So what we have stress we had put it as P by A. When this area is reducing, the stress will also increase. Okay, if we are able to measure the change in the diameter at every instant of the stress, this is actually the curve what will come, and the specimen will fail over here at a stress much higher than the yield stress. That is where the specimen actually fails, and that is what we call it as a true stress. Okay, true stress. What we are plotting here in this stress strain diagram by conducting the test, it is not the true test, the true stress. Okay, it is the nominal stress, because we are every time we are putting this with respect to the original area. Every time in the table you calculate the stress, the area what you will take is the original area what we have measured. Before the test I have measured the area of the specimen. Okay, I'm using the same area for calculating the stress at every point of test. But what is happening actually in the stress specimen? The area is reducing. Okay, you can see here we call this phenomenon as necking. At some point where the specimen is weak, okay, so it will be forming that neck shape. You'll find that reduction in the area is more at that point, or reduction in the width or the diameter of the specimen will be more at this point. Okay, so this is the necking phenomena what we'll observe there. Now if you are able to measure that reduction in that diameter, and if I express that here, if I take that area into consideration while calculating the stress, you'll find this curve. You'll be able to achieve this curve. What you'll plot, you'll get this curve here. Okay. But what we are doing is, since we are using the original area only for every calculation, we are finding that failure stress is lesser than the ultimate stress, or else the fracture stress will be more than the ultimate stress in true curve. Okay, so keep in mind this is the true stress strain diagram. If you use original the area, actual area, it will give you the true stress strain diagram. But what we are using is we are using the original area of the specimen, so we are getting this nominal stress strain curve. Okay, so these are some points what you need to know in this stress strain curve. Okay, so this will help us to uh, predict the behavior of the member of the structure based on whether it is in proportionality limit, the materials are stressed within proportionality limit or beyond the proportionality limit. Accordingly, we'll be using the properties from this stress strain curve. Okay, so that is one thing. Now another thing is, in this, if you find this slope of the linearity range, slope of this line, okay, so that will represent the Young's modulus E, because what you are finding here is this is strain, this is stress, so this will be equal to stress by strain. So this will be the Young's modulus E. So this test will yield you certain results regarding the material. What? One is Young's modulus. You will be able to calculate what is Young's modulus of the material. Then it will tell you what is the yield stress, at what particular stress the material will start yielding. Then it will also tell you what maximum stress it will take before failing. Okay, ultimate stress it will tell you. Then it will also tell you what is the rupture strength or the stress at the failure. At what stress it will fail, the material will fail. So these are some properties and uh, the test what it will tell us. Okay, and the phenomena of necking, that is very clear in case of ductile material. Okay, so is that okay regarding the stress strain curve? So these points you need to understand that. Okay, just forget this partially plastic. I have taken the picture from one of the images from search page, but just leave it partially plastic and all, not required. So only thing is this A to F, these points should be clear to you. I'll be continuing this class in the afternoon. I'll send you the link. Okay. As of now, I'll stop over here. We'll meet in the afternoon. I'll communicate it in your group. And please join that Strength of Materials official group. All the notes, videos will be shared on that group. Here. Okay. I'll end the meeting. We'll meet in the afternoon further. Yes, sir. Hoguna.